As you've worked through calculus, you've seen how it can be used to compute derivatives, areas, arc length, and surface area. And here we're going to look at how we can find all four of those through the lens of parametric curves. We'll start with derivatives. For x equaling f of t and y equaling g of t, if y is a differentiable function of x, then we have that dy dt is equal to dy dx times dx dt. That's by the chain rule. We're saying that y depends on x, but in turn x depends on t. Solving for dy dx, we get that dy dx is equal to dy dt divided by dx dt. And that can be expressed as g prime of t divided by f prime of t, because y depended on t, we called that function g, that's g prime. Likewise, x was defined to be f of t, and so dx dt is f prime of t. Of course, we have to have that dx dt is non-zero because it is in a denominator. The second derivative isn't quite so straightforward. d2y dx2 is the derivative with respect to x of dy dx, and so is equal to the derivative with respect to time of dy dx divided by dx dt. Now I know this looks a little bit weird, but what we've really done is we've taken in the equation that we just came up with, the expression dy dt, we simply replaced y by dy dx. Using the Leibniz notation together with Newton's notation, we have d dt of g prime of t divided by f prime of t, all divided by dx dt. So it's the second derivative of y as x changes, but we really aren't saying that dx dt is changing itself, right? So y is what's changing. And so that's why the additional derivative portion thingy is in the numerator. And then I'll box this up. We'll see how these formulas are applied in a different video, but for now we're just going to move right on to areas. Recall that the area under a curve is given as the integral from a to b of f of x dx, and it's the area provided that f is a positive or non-negative function. This can be rewritten as the integral from a to b of y dx. If x is equal to f of t and y is equal to g of t, then for t between alpha and beta, the area is given by the integral from a to b of y dx. Not new, we just wrote that down. But in terms of t, it's the integral from alpha to beta of g of t times f prime of t dt, where we are considering that x is f of t, and so dx is f prime of t dt. Y is g of t, and so y is simply replaced by g of t. That gives us area for parametric curves. On to the next. Arc length. Recall that we have a formula for arc length. It is L is equal to an integral from a to b of the square root of 1 plus, that's not a 1, 1 plus f prime of x squared dx. So if we have x is f of t, y is g of t, and t going from alpha to beta, and if dx dt, which is equal to f prime of t, is positive, then L, which equals the integral from a to b of what we just said, the square root of 1 plus f prime of x squared dx, becomes the integral from alpha to beta of the square root of 1 plus dy dt divided by dx dt squared dx. Our input variable, though, is t for our functions. Y is f of t, x is f of t, y is g of t. So let's introduce a dt here, the differential of t, and I'm actually going to multiply and divide by dt here. So we have tacked on dx dt dt. If we then distribute dx dt into the square root, first of all, we have to square it on its way into a square root, and then second, it's going to reduce the fraction that we have inside of the radical. We'll end up with L is equal to the integral from alpha to beta of the square root of dx dt, the quantity squared, plus dy dt, the quantity squared dt. This is also written as the integral from alpha to beta of the square root of f prime of t squared plus g prime of t squared dt. For our last formula, I know it's going by so fast, right? Surface area. For a curve C given by x is equal to f of t, y is equal to g of t, t between alpha and beta, where f prime and g prime are continuous, and now g prime of t is not negative, rotated about the x-axis. The surface area is given by the integral from alpha to beta of 2 pi y times the surface area dx dt squared plus dy dt squared dt. Rotated about the y-axis, we have that s is equal to the integral from alpha to beta of 2 pi x times the square root of dx dt squared plus dy dt squared dt. In these cases here, about the x-axis, y is playing the role of the radius, and about the y-axis, x is playing the role of the radius. Now, of course, since our differential is dt, and this is single variable calculus, our square root is going to have an expression that only involves t. So having this y here is a little bit weird. Remember that y is actually given by g of t. And then for the other formula here where we see an x, remember that x is actually given by f of t. And so we'll only have expressions involving t in our integrals here. And now I'll put this in a box. And the rest of the videos in this section are going to be applying these formulas.